In 2.1c, we're going to find the standardized value, which is called the z-score, and then we're going to interpret the z-score in context. And z-scores are one element that we're going to use basically for the entire book. The one thing we need to do in statistics is to standardize our data, especially if we're going to compare one data set to another. And what that means is we standardize so we don't compare what we would say is apples to oranges. A nice real-life example of that would be, what if I'm analyzing a track team on how they did, comparing their hurdles event to their 100-meter run event. You can't really compare the two, but if you standardize their data, then you can. So standardizing is going to help us show how different a value is. This right here is the formula for a z-score, and what it is it's going to tell us how many standard deviations, which down here is our sigma. A piece of data is from the mean, which is our mu here. And back in this formula, x is just the piece of data that we're looking at. Now, what if we use this calculation? Again, let's talk about our time on the hurdles. If I took my time on the hurdles minus the mean of the team divided by the standard deviation of the team, and what if I get a positive z-score? What does that imply? Well, it implies that the data is above the mean, versus if we compute and we get a negative z-score, again, my piece of data minus the mean, if it's negative, I'm going to be below the mean for this one. Now, let's talk about units of measure for that. Assume we're looking at class data and heights are in inches. What is the unit of measure in terms of each of these? So if we compute the mean of the class in inches, then we know the unit of measure of inches. So over here is the mean, so I'm just going to put inches over here, little in for the label. Standard deviation would also be in inches, so we can state that, and I'm going to put the label of inches here. Now, if we put our piece of data here, my own particular height, that would be measured in inches. And if you think about it, if you do the calculation on the top, the label on the top is going to be something in inches, and on the bottom we still have inches. So what's going to happen, technically, the labels cancel out, which means the z-score actually has no unit of measure. No matter what you use for your calculation, if it's test scores or heights in terms of students, the units of measure will always cancel out, so there is no direct unit of measure if you compute the z-score. So let's look at this example. We have a particular teacher's class in terms of, they said, where do I stand? What are your heights? Down below here we have a dot plot of the height distribution of the students in this teacher's course, along with some output. So I think you have the computer output on your screen. So here n is how many pieces of data. There's 25 dots. X bar is the mean height of 67 inches. S of x is the standard deviation of the sample, which is 4.29. So I can adjust this particular z-score. This mu is meant the population mean. Sigma is the population standard deviation. Now, if they just give me a sample, that means I'm going to do x bar, because this mean is for the population, that's for the sample. Conversely, the standard deviation is S of x, so this is the population standard deviation, that's the sample. So these two would just adjust accordingly. Now, if they want us to find Lynette, a student who's in the class, is 65 inches tall, find and interpret her z-score. So it's very easy to compute a z-score. Again, we're just going to take the piece of data, in this case 65 inches. The class average was 67. And then I'm going to divide it by 4.29. Go ahead and get your calculator out on that. Remember to do this calculation first, then divide by 4.29. And we're going to get a negative 0.466 as your z-score. Now to interpret that, what it would mean is that the definition, Lynette's height is 0.466 standard deviations below the class average. So that by definition is what a z-score implies in this particular case. Now there's another student, Brent. He's 74 inches tall. How tall is Brent compared to the rest of the class? And give an appropriate numerical calculation. Easy enough, we're just going to compute Brent's z-score. So his z-score is going to be 74 inches minus 67 over the standard deviation of 4.29. His z-score is going to be 1.63. So if we look at that, he is 1.63 standard deviations above the class average in terms of height. The last question here, Brent's a member of the school's basketball team. The mean height of the players on this team is 76 inches. Brent's height translates to a score of negative 0.85. What is the standard deviation of the team members' heights? Well, we can go ahead and compute this. It's not too difficult. We're just going to kind of reverse the z-score. We know his z-score is negative 0.85, and that's going to be equal to his piece of data, or his height, of 74 minus the mean of 76 over some standard deviation calculation. So if we go ahead and simplify and solve this, we're just going to have a basic equation here. I'm just going to go ahead and do some cross multiplication on here. So therefore, we're going to have a standard deviation. It's going to be negative 2 over negative 0.85. And if we simplify this down, we're going to get 2.35 inches, which means on average, a member in the team deviates by 2.35 inches from the typical player. Let's look at one more example, since this is such a standard concept in this book. Here we have a track example. We have competitors A, B, and C all competing in a decathlon. After 3 events, who turned out in the most remarkable performance in the competition? So what we want to do is compare performance of a 100-yard dash, the shot put, and the long jump, which clearly aren't comparable events, so we have to standardize their scores. Now, in this table here, we do have standard deviations and means for all of these events. So what we would want to do is to figure out who has the best score or performance in each of these events, and then compute the z-scores for the 3 and decide from there the competitor that is the best. So for the 100-yard dash, if you think about it, you want to have the quickest time, so the 9.9 seconds, competitor B. For the shot put, you want to be the furthest, so 66 inches is the best. And for the long jump, you want to be the furthest. So we actually have, as it stands, each competitor is the best in one of the events. Let's compute the z-scores for all 3 of these events and see who deviates more on average. So I'm going to do the 100-yard dash. Let's do that first. So the z-score, and I was going to put up 100 there. I'm going to take the score of 9.9 minus the mean of 10 seconds, and if we divide that by 0.2, we're going to get a z-score of negative 0.5. So in terms of the 100-yard dash, you are below the average, which is a good thing. Okay, the next one, let's take a look at the shot put. If I compute this for the shot put, let's do the z-score. I'll just put the shot put. That we're going to do the 66 inches minus the 60 over the 3, and that's going to give us a z-score of 2.0. So as it stands, just to compare these two right now, clearly the shot put z-score is better because there are 2 standard deviations above, and in this case above is the direction we want for the shot put, below is what we want for the 100-yard. Now let's wrap it up with the long jump. So the z-score for the long jump in this case is going to be 27. I have to change the 3 inches to 0.25 feet, so I'm going to make it comparable. Minus 26, and then 6 inches is 0.5 feet. So as long as we have the same units of measure here. And when you do that, you're going to get a z-score of 2.5. So for this one, our winner, therefore, is going to be the individual with the long jump. So we would say competitor C had a better performance because there are more standard deviations. Again, either above or below, you have to think of the context of the problem. For the long jump, you want to be above. Again, for the 100-yard dash, below would have been good. If the 100-yard dash had come in at a negative 3 z-score, this would have been the best competitor. But for here, it's the long jump, therefore competitor C.